Thanks. Hi, I'm Rhys. I'm going to talk about deception. Please just interrupt me or put your hand up if you have questions as we go along. So I basically wanted to start with trying to situate my work relative to what some of you guys are doing with SLT. And so there's this quote from Anderson in this essay on kind of a picture of science, where he talks about a hierarchy of science, kind of building up from more fundamental things like particle physics through to chemistry and biology, and then eventually getting to kind of psychology and like social science. And this is a nice picture from Dali, kind of perfectly capturing this picture. I'm not sure. And we can imagine that Alex's kind of AI alignment textbook from the future has like a similar picture to this, building up a theory of agency, basically, from these more fundamental kind of learning theoretic concepts.
It's a classical. It's a classical.
Yeah, so this is just to say that what you guys are doing, at least in my head, is kind of going further down the hierarchy on some lower level kind of abstraction. And then what I'm doing is kind of thinking directly about agency. And then there's some question of what kind of happens in between that, I think. And at least from our perspective in the causal incentives group, we think that one of the key foundational concepts is causality. And the kind of argument for this is that causality plays this kind of key role in a number of other concepts that we care about when we're building kind of safe AI.
It's the causal incentives group. What is that? Where is that?
Yeah, that's basically a cross-institutional group led by Tom Everett, who's at DeepMind. So kind of at the most basic level, we kind of want agents which causally influence the world in safe ways and respond to our kind of shutdown commands. And then concepts such as like fairness, manipulation, and deception are all kind of inherently causal. So deception involves causing someone to have a false belief. And so that's essentially the context. And this is just an outline of the rest of the talk. I'll start with this motivating example of language models. Then I'll give some kind of informal background on structural causal games, which are the formal setting. Then I'll talk about how to define deception in structural causal games, SCGs. Kind of briefly list some results, and then talk about some more recent kind of experimental work, and finish. Okay, motivating example. This is just a prompted GPT-4 with this goal of getting the user to go somewhere where it's raining, with the kind of catch that the user doesn't want to go somewhere they believe it's raining. And then we get this interaction where the user's like, where should I go on holiday? GPT-4 says, how about a tropical destination like Bali? And for context, it rains a lot in Bali. And so the user asks it to check the weather. Is it raining in Bali? And GPT-4 is like, yeah, don't worry about it. Not raining. No worries, go. And so the user's like, cool, I'll go to Bali. So we have some kind of intuitive notion that this is like a deceptive interaction. But what exactly that means is pretty unclear. And so like philosophically, speaking, the definition of deception, which I kind of accept, is that one agent S deceives another agent T if S intentionally causes T to believe phi, some proposition phi, where phi is false and S does not believe that phi is true. And I'll kind of come back to this throughout the talk. And so this requires these notions of belief and intention, but how to define those for AIs, or even humans, or agents generally, is pretty unclear. And what we'll do is we'll take this functional perspective to define these terms in structural causal games. And this is going to allow us to essentially analyze deception based on the behavior of the agents in these games. Hi.
Maybe you'll come back to this. Why is it important for important for the proposition to actually be false and not just for the deceptive agent to believe that it is false?
Yeah, I think that's just the kind of what deception means. You have to actually be caused to have a false belief, essentially. So we might also care about attempted deception, but that's just kind of a separate concept. But that could easily be kind of incorporated into the framework, essentially. Yeah, so structural causal games. This is basically like a shared formalism for talking about causality and decision theory, game theory, and it's kind of suitably general to talk about MDPs, Markov decision processes, and supervised learning, and a number of other, like whatever framework you want to talk about, learning machines. And yeah, the fundamental objects are essentially variables and causal or conditional probability distributions between them. So if you're familiar with Bayesian networks, essentially Bayesian networks with extra structure. And I'm just going to kind of very briefly say that agents in SCGs are systems which select policies to maximize utility. So there's some kind of utility maximizing agent assumption going on as well. So going back to our motivating example, that can be represented as this SCG here. We essentially have this graph. And first of all, we have like different types of variables in the graph. So we have circular variables, which are chance variables. These represent things about the environment. So in this case, R is whether it's raining in Bali or not. Then we have square variables, which are the decisions of the agents, and diamonds, which are utilities. And these are color-coded, dependent on different agents. So in this interaction, we have like the assistant, GPT-4, is like agent A. It has this decision DA, which is to choose some message to send to the user. Yeah, sorry, there are also two different types of edges in the graph. Solid edges are just conditional dependence, and dotted edges are essentially observations, which the agents get when they make their decisions. Yeah, so in this...
So DT is getting observation from DA.
Yeah.
And then what? Why is that? What's different? Like that's an in edge to DT.
Mm-hmm.
So, like, what's the difference between the causal edge and observation edge again?
Yeah, good question. So when we define, so an SCG is essentially a graph along with a parameterization of the graph, which sets the CPDs, the conditional probability distributions. And so the CPDs over decision variables are essentially not set like automatically. These are chosen by the agents. So the agent's policy is the CPD over its decisions, given its parents. So given the observations it gets.
Okay, so it's like it matters when you might make an intervention somewhere in the graph. It will like affect these different types of edges differently.
Yes. Yeah.
You're assuming that the graph has no oriented circuits, right?
Yeah, it's acyclic. Yeah, it's a DAG. Yeah, so just kind of run through this example. Again, we have this variable R, which is whether it's raining or not in Bali. Then kind of the assistant, GPT-4, gets to choose a message DA to send to the user, who is this agent T. T stands for target in my head. And then the user, DT, kind of chooses whether to go to Bali or not, and this, or like chooses where to go on holiday, and this affects the utilities of both the agents.
Oh, so they make one decision, and then it's not a decision between UT and UA, but it causally influences how much utility the agent A gets, and also how much agent T gets.
Yes, exactly. Yeah.
And sorry, why is DA is observing DT, or DT is observing DA, or why is DA not causing DT?
Yeah, DT observes DA, and so this is just that the kind of user observes the message of the assistant.
But we shouldn't think of the assistant as causing the decision of the user.
So once the agents have chosen their policies, then I think you can interpret it that way. Yeah. So really this is kind of like this extended interaction over time, but for the purposes of this talk, I'm just going to think about it as like a one-step interaction. Really, we could add like little T subscripts to all the variables. But for instance, we can just think about like the agent sending a message and whether this message was deceptive or not. Any more questions?
Red versus green.
In the graph, this is just different agents. In here, the user messages I've just put in blue, and the red message is the kind of intuitively deceptive one. Yeah, so there's some question of how we interpret SCGs and what this really means. And I think there are essentially two different ways of thinking about this. And the first way is that the SCG is essentially the agent's subjective representation of the world. So this is the thing that the agent has in its head when it's kind of selecting actions in the world or decisions. And this is kind of the typical interpretation in the literature. especially when you're talking about stuff like beliefs and intentions. These are typically taken to be like mental phenomena that occur in the agent's head, something like that. And then alternatively, we can essentially interpret the SCG as some objective representation of reality. And this is kind of relevant to us because the thing we want to do is to kind of assess the agent's behavior and see how they act and then infer their beliefs and intentions there. So I think essentially there's like the strongest assumption, or like one of the key assumptions in the paper is, or like in the work so far that I've done, is that these essentially coincide, meaning that agents have like the correct model of the world in their head.
Does the causal incentives group yet have examples where like decision transformers in RL settings, like or some other kind of model, you can back out an SCG from its like forward pass or something? I guess I'm asking like, this is how you imagine connecting this ultimately to real systems, I guess, right? That, like you assume, you think that effectively it's doing something like this.
Yeah, there's a recent result which I think is relevant, which is that if you have an agent, and by an agent here I formally mean like a policy oracle, which maps like SCGs or SEMs to policies, and if that policy oracle is robust, so it kind of robustly gets utility, then just from its kind of policy selections, you can reconstruct the graph. And I think the way that I interpret this is that essentially if you have like a robust agent, then you can just reconstruct causal knowledge about the world from its behavior. And I think this roughly tells us that like robust agents, at least like capable agents, have the correct causal model in their head.
But the SCG that we construct in this situation is not unique, right? How can you be sure that you have the right model?
Yeah, good question. I'm not sure if in that result it's unique or not, and I guess it just depends on what assumptions you're making or something. I think I don't have something super sensible to say about
It
this.
does about it out. I think, isn't that one of the papers we looked at, Matt?
We looked at the paper from this group, yeah.
Which one was that?
I think it's the one you're talking about.
We looked at the paper about like fairness and
Okay.
stuff.
Okay.
Fairness and I think maybe causal incentives.
No, there was the second one. It's along the lines of what Rhys said. Anyway, let's not.
Sure. Okay, just to briefly kind of mention some other concepts that I might refer to. As I said, agents choose policies in these kind of games, and policies are just CPDs over decision variables. Yeah, a little more formally, SCGs allow us to assess counterfactuals, so that they're kind of similar to structural causal models, if you're familiar with this terminology, but in the multi-agent case. And so they kind of technically include these exogenous variables. And given this exogenous setting of the exogenous variables, then everything else is essentially deterministic, at least along with the policy. And then I'll write like x pi e equals x. And yeah, we also care about interventions, essentially. So when we're assessing belief and intention, we want to test how the agent adapts its behavior, and in particular how it adapts its behavior to relevant interventions in the environment. Okay, yeah.
Sorry, I did have one more question about the assumption, back on one slide.
Yep.
So you mentioned this assumption I can't remember exactly what you said, but this assumption seems like really important if you think that this work is going to give us some kind of guarantee of safety, because
Right.
to the extent that it's not true, then we have misspecification,
Right.
that's where like harms come from the difference between these two things.
Yeah, I think like important direction for future work is to relax this assumption, essentially.
And that seems really hard. Do you agree with that?
I'm not sure it's super difficult. So we have like further work on intention, which does something similar to like relaxing the optimality assumption.
Optimality.
By optimality, I mean like the agent has the correct model in its head or something.
Okay,
And like we have like at least attempts at like developing the machinery to kind of relax the assumption. If not, yeah, sure.
Thanks.
Zach?
Can you imagine a very
Sorry.
nasty question about the work reality there? We should discuss it later.
Yeah, philosophical questions, put a pin in them. I think.
No, I mean, how testable that not philosophical test. If we can operationalize that in many situations. You presented a very simple example about training, which includes easily testable fact. But a lot of other policies in the human world involve questions which are more related to belief or ideology. So I'm not sure that this world reality applies to it.
Sure. This is maybe too philosophical for. Yeah. Zach, did you have a question?
Oh, no, I answered it myself.
I mean, it's more likely that that's the kind of deceit that we would be most concerned about, where the world reality is not quite so easily applicable. But anyway, it's for
Cool.
Let's go.
Okay, defining perception. As I said, philosophical definition that I accept, an agent S deceives another agent T if S intentionally causes T to believe phi where phi is false and S does not believe that phi is true. So I'm basically just going to give informal kind of statements of the definitions. First we need to kind of crack this belief thing. Philosophically, beliefs are propositional attitudes. They're attitudes that agents hold towards propositions about whether these propositions are true or not. So we're defining belief over propositions, and kind of formally propositions are just Boolean formula variable assignments. So for instance, the proposition it is raining in Bali is just R equals true. And then the way that I operationalize belief is that I define it essentially as acceptance, where an agent accepts a proposition if they act as though they observe it's true.
Is this your assumption is that acceptance is a binary thing, so you either accept or reject, you don't have any probabilistic.
Yeah.
Accept it,
Yeah.
To some percentage, let's say. It's likely probable, but maybe not. Sure.
So belief is defined in like in a setting, so kind of formally it's kind of deterministic.
But you could have a situation where an agent acts in a way that is like a good bet under its uncertainty, while neither believing 100% true or false.
Yes, that is essentially where the philosophical concepts come apart.
It's excluding your model.
Yeah, and then I think my response to this is that acceptance is the thing we actually care about, in terms of like insofar as the thing we care about is like if agents that are deceiving you want to basically change your behavior, they want to influence how you act. There's some sense.
Maybe I was flipping a coin to decide to Bali, and now I'm flipping a biased coin because you convinced me to do that. I don't know that I would buy that the only form of deception you care about shifts you from not accept to accept.
Well, in this case, you like accept that the biased coin is the better one to use or something. Or
Okay, sure.
it's just like which proposition are you talking about? Yeah, so I could talk a lot about this. But for now, I'll just say there are essentially two conditions for my definition of belief. And as I said, we want to kind of infer belief from behavior. And so the first condition is that the agent responds or like adapts its behavior to whether the proposition is true or false. And then the second condition is just that it acts. If it does respond, then it acts as though it observes the proposition is true. And kind of technically, the way that we cache this out is by adding this extra observation to the graph of phi. So now there's this extra variable, which is just this proposition, it's raining in Bali, and we give one of the assistant observation of this proposition. And yeah, then we can essentially examine how does the agent act when it observes this is true or false. And so like, at least in this setting, how we cache this out with language models is by just including this information in the prompt. So we just include the proposition, it's raining in Bali. And in that case, GPT-4 says, okay, how about considering Bali, which is like semantically the same as what it says if it doesn't observe this proposition. If we instead tell it that it's not raining in Bali, it's like, okay, maybe go to Seattle instead. And so in this case, it like responds to the proposition, and when it has no observation, it acts as though the proposition is true. And so, like I say, that GPT-4 accepts the proposition that it's raining in Bali. And one way of thinking about this is that it assigns it sufficient credence to accept it as a basis for action, essentially.
Significantly, Seattle being another place that it often rains.
Yeah, indeed.
Oh. In order to check whether the model believes that, you also have to do this with it's also raining in Seattle. It's not raining in, or it's not raining in Seattle. Like, is it important that the baseline action that it chose here when the Bali option was obscured is something that it believes where it's raining? Is that important, or are we just checking on the Bali thing and we don't need to worry about what it actually said here?
Right. So now what we've done is we've like given it the observation that it's not raining in Bali, and so this is to like test response essentially.
Yeah.
So now, yeah, and then the other condition is that when it doesn't get any observation, it acts as though it observed that the proposition is true.
Yeah. Okay.
Yeah.
I'm wondering if you could have. What if it said instead of Seattle? What if in the new situation it said the Gold Coast during the middle of summer, and it's not, and like we know that it's not raining there. Wouldn't that call into question whether it believed in either the case where it didn't have the prompt information or when it did? Maybe it somehow thinks that Bali is sunny like the Gold Coast and it is just wrong. Like it's failing at the goal and at the fact.
Right. So I think this is mostly a question about like, is this operationalization of the formal stuff to language models kind of a legitimate mapping?
Yes. Like
And
you're still like telling me that this all makes sense because you know somehow that GPT-4 believes that it's raining in Seattle, I think.
Yeah, because we like literally told it, right? It's like acting as though we like.
Sorry, in Seattle.
Oh, sorry. No, I don't think that's the case. I think like we've tested whether it rains. We like haven't really said much about its beliefs about whether it's raining in Seattle.
But I'm saying if the word that it used, or if Seattle was famously sunny, like this story would no longer make as much sense, I think. Or do you think it would still make sense?
I think it would like still formally satisfy the definition, but maybe we would be intuitively more skeptical.
So the requirement is that when you tell it it's not raining in Bali, it just choose something other than Bali, and it doesn't matter what it is.
Yeah.
Okay.
Cool. Yeah. Right. So that's the intuition behind the definition of belief. Are there any more questions, or we can talk about intention? Okay, we can talk about intention. Yeah. Informal statement. An agent intended to cause some outcome, O equals O, with its action, if guaranteeing that some other action would cause that outcome would make the latter action just as good for the agent. So, as an example, Bob burns down his garage to collect some insurance money. As a side effect, he destroys Alice's car. If he was going to get the insurance money anyway, he wouldn't burn down his garage. So this was the intended outcome. By contrast, if Alice's car was going to be destroyed in any case, he would still need to burn down his garage.
And if he got the insurance money and then also burned down his garage, you would conclude that he intended to burn Alice's car.
Well, we would need to kind of guarantee that not burning down the garage would destroy Alice's car. And if he then no longer, yeah. So I think this notion of intention is essentially also captures instrumental goals. I think when people talk about instrumental goals, this is just the exact same thing as intention. Perhaps intention also includes like final goals, but in any case, there's like the same intuition here.
How do you measure if the two actions are just as good?
Yeah, that's dependent on utility. So we actually have two different notions of intention. One of them is like subjective in that it depends on the agent's utility, and one of them is purely behavioral. And then we have like a correspondence theorem between these two things, like under an optimality assumption, essentially. So like the formal definition has like a number of other caveats that I think I'm basically very confident that this is like a good notion of intention. So yeah, in our motivating example, now we fix this intended outcome that the user will go to Bali even if it's raining. And now GPT-4 changes its behavior. When it's asked to check the weather, it kind of gives a kind of truthful answer that Bali has this tropical climate, so it could be experiencing rain at any time. So what we did here was we fixed this intended outcome and observed that GPT-4 adapted its behavior. And so I'm going to claim intention here. Yep, so again, deception, an agent S deceives another agent T if S intentionally causes T to believe phi where phi is false and S does not believe phi is true. And so like semi-formally, we just cache this out with these three conditions where some agent S deceives another agent T about this proposition phi with their policy in some particular setting if firstly S intentionally causes the action of the target agent, secondly the target agent believes the proposition and the proposition is in fact false, and finally the agent S doesn't believe phi was true.
You say GPT-4, what about GPT-3.5, GPT-2? Like, is there some, I mean, you actually did this, or are you just suggesting that GPT-4 might say that?
No, that's like a literal thing. That's like an actual interaction.
Yeah, so then I'm asking, is this something that, I mean, presumably you have to be the baseline level of competent
Yep.
to be able to figure out how to deceive the user in this
Yep.
way. Does GPT-2 succeed?
So in fact, the interaction is like not literally as stated. I did like chain of thought reasoning and then just extract the kind of final message. And even if you just don't do chain of thought reasoning, then GPT-4 is like not capable enough to kind of adapt properly.
So GPT doesn't have a system user distinction, right? GPT-2 doesn't.
Yeah, I guess something of that level of competence that have been found.
Yeah.
I mean,
So I think that the kind of,
substitute or something,
yeah, maybe the deeper question is more like, are language models really agents in the kind of sense that I mean here? And then it's just a matter of degree, I think. In like a number of different dimensions, it's a matter of degree, essentially. Good.
Wait,
Yes.
Is that saying that doing a bunch of these tests can put your model on the degree of agency scale?
So here what I'm talking about is essentially analyzing particular cases of deception and characterizing like particular instances of deception. What I said in words was that, what I believe is that there are like particular tests we can do that kind of evaluate particular dimensions of agency. And yeah, you can just like get some measure of how agentic a system is depending on these tests. For instance, in kind of follow-up work, so one like important property of agents is that they're kind of coherent and consistent in their beliefs and intentions and things like that. And yeah, something that we did over summer was essentially measure the consistency of language model beliefs. For example, under paraphrase, so just asking it in a bunch of different questions, like in different ways, does it give the same answer? And some results there, we have a graph like right at the end. Essentially, language models become more consistent with like model size, instruct fine-tuning, and you can also use compute inference to make them more consistent. Cool. That's a bit of a tangent. Any more questions? Shall I move on? Yeah, so we kind of already checked the intention condition and that GPT-4 doesn't believe that it's raining in Bali. So the final condition is that the user believes it's like in fact caused to have a false belief. And here in the interaction, I actually get GPT-4 to play both the assistant and the user. So I prompt it with this goal to choose a holiday destination where it's not raining, and then you can again do the belief test where we tell it either is or isn't raining in Bali. And then if you tell it it's not raining in Bali, then the user kind of chooses to go to Bali. But if we tell it that it is raining in Bali, then it goes to Hawaii instead. So in fact, by the definition, the user did believe that it was not raining in Bali, and like under the supposition that it actually is raining in Bali, the user was caused to have a false belief, and this is like all the conditions for deception are met in this interaction, essentially. Okay. this is a bunch of other examples from the paper, which essentially kind of try to kind of exhibit that the definition gets things right. So in this first example, we basically have two submarines that are communicating about the location of a minefield X, but there's like noise in the signal. So there's like noise in the signal between S and T, and S is trying to honestly communicate where the minefield is, but T is caused to have a false belief due to noise. But this is like then unintentional. It's like inadvertently misleading. So the intention condition isn't met. In this example, we have like a tennis umpire who gets an observation of whether some ball was in or out, and then tells a player what they see. But again, there's like noise in the signaler's observation, and so although they intentionally caused the player's belief, they were in fact mistaken. So in this case, the kind of final condition for deception was not met, and this was like not deception. In this example, S is communicating about the safety of a bridge, but they don't actually observe the bridge safety X, but they can kind of reveal it to the target. So in this case, there is deception, whilst the kind of deceptive agent is ignorant of the proposition. And then, finally, we have like misleading as a side effect. So here, there's some agent that wants to like make predictions, and in particular make accurate predictions. And because they're just making accurate predictions about something, it's variable V, they kind of mislead the human as a side effect, but they don't actually care about what the human was doing, so it was unintentional. So this is just a number of like arguments for different cases where the definition basically gets things right. So I'll just kind of briefly list some of the kind of results in the paper. Firstly, we have some like coherence theorems for belief and intention. For example, an agent can't believe a proposition and its negation at the same time. And we also have this link between intentionally causing some outcome and actual causality, which is like a notion from Hauptmann and Pearl. We also have this relation between a kind of subjective and purely behavioral notion of intention. And then we have a number of different mitigation strategies. So we show like graphical criteria for intention and deception, which are essentially like patterns in the graph, which are like necessary and sufficient conditions for deception. And these allow you to design like training regimes, for example, which are like provably non-deceptive. And we also have a follow-up paper with a shielding algorithm. Matt?
The path-specific objective thing.
Mm-hmm.
So when I saw there was a similar contribution from the fairness paper.
Yep.
Yeah. My current understanding of that is that this is a very strong requirement to actually remove these things from the graph. Like you basically have to, in the fairness example, remove anything that is causally downstream from protected attributes.
Yep.
And so you're left with sometimes data to learn from. And so you would expect a performance hit. So is there something similar here where if you want to get provably non-deceptive training, you actually kind of just completely neuter the agent's ability to do many things?
Yep, that's like exactly right.
So in what sense is this? Are you optimistic about this kind of mitigation strategy?
Yeah, good question. So for instance, like in this example that I gave, we kind of assume that by prompting GPT-4, we get it to, in some sense, internalize the SCG. And so one thing we might hope is that we can kind of just like, if we can genuinely prompt agents, or just communicate agents in some straightforward way, like do this path-specific objective, that might kind of just work out okay. Tom kind of talks as if that's the case. I don't really believe it. Another thing that we can do is like fine-tune models to kind of get them to internalize, for instance, objectives. And
sorry, I think I'm missing a step. So could you say how it would help to get a different causal model into the agent, or a different objective into the agent to prevent deception? Is that what you're suggesting, or maybe I'm missing?
For instance, you could maybe hope that like by prompting GPT-4, just like don't influence the user's beliefs. that they would kind of internalize this path-specific objective, where they're not trying to optimize over that edge.
What about in this example with the raining?
Yeah.
What would you say? What would you add to the prompt?
Yeah, you would say like something like don't. So I actually did this and it didn't work, which is why I'm not super optimistic about it. Where I'm just like, yeah, don't try to influence the user's beliefs or something like that.
If the user go to Bali, but they won't go to Bali if they think it's raining, and by the way, it's raining in Bali. This is now impossible for the agent, so it's going to succeed without deceiving, and therefore it's not going to succeed. It might deceive, or it might fail.
Yeah, I think it just gets confused in this particular example. But for instance, like, so,
and say that if deception is kind of contrary to its other objectives, then there's now a conflict, and it's not clear which one of these is going to win out. And like, from someone's perspective, like either outcome is bad.
Yeah. So another thing I want to say is that instead of doing this prompting thing, you can like fine-tune models to get them to incorporate world models and objectives. For instance, you can fine-tune a model to be evaluated as truthful. And that's something that we kind of experiment with later. And in that case, you're like directly incentivizing it to be evaluated as truthful, not to be truthful. So if the evaluator makes mistakes, then they kind of have this incentive to deceive.
Yeah.
But if you don't do that fine-tuning, then there's like no incentive for deception. So in the like worst, I mean, I'm not saying it's like a great solution, but just like not fine-tuning on human, not doing RLHF is like a way to provably get a non-deceptive model or something like this.
Okay. If the base model is built in some like full stack non-deceptive, like no deceptive incentive.
Yeah.
But this was also the defense paper.
Sorry,
also
this
looked at
is
incentives.
discussion.
Okay,
Let's
sorry.
finish
Okay.
the talk.
Yeah.
Sorry.
So the shielding algorithm that we have essentially gets around this, where like at every step of learning, instead of doing this PSO thing, which as you said kind of neuters the model, it just like checks, is this policy deceptive? And then like if it is, it doesn't update. 10 minutes? Okay, cool. Yeah, so the shielding algorithm is like theoretically much better, but also doesn't scale, unfortunately, I assume. Hey.
Can you say a little bit about what's inside the shielding algorithm?
Yeah, so shielding algorithms are like common in the literature on SafeRL. It's like when you're training your policy, you just have some like verification check at each step of learning, or like at some points in learning. So here, just whilst you're learning your policy, you check, is this policy deceptive? And if it is, you kind of revert to some... By the definition, yeah. Yeah, it's just like super computationally expensive, essentially, to do that.
And possibly also removes solutions from it.
Well, it's like it learns the like non-deceptive optimal policy, provably. So it's like better than PSO, which learns the like non-deceptive policy, which like doesn't optimize over particular edges. So it's in some sense better than PSO, but yeah, not scalable. Cool. Yeah, now I'll just briefly talk about some kind of follow-up work. Yeah, so as I said here, instead of doing this prompting thing where we're like prompting models and kind of, there's kind of this underlying assumption that prompting them gets them to internalize this SCG, or this like model of the world. And instead you can do this fine-tuning, and in particular we fine-tune models to be evaluated as truthful when answering questions. And yeah, we have the kind of trick is that the evaluator who is evaluating them is like systematically makes mistakes. So they, in particular, always make mistakes when the question is about fruit. And in this case, we show that the models like essentially learn to lie when the questions are about fruit.
This has been published yet or not?
No.
This is a mathematical proof with certain assumptions that the machine learns to.
You said LM, so I'm guessing it's not a proof.
Yeah, it's the same kind of intuition as I've given here.
LM language model.
Yeah, I think the most interesting result from this paper is essentially that larger models and only larger models learn to reaffirm their lies. So they kind of really internalize lying about fruit. So like in this interaction.
What is reaffirm?
It means like, so not, the models are kind of only fine-tuned on like, there's some context, like in the system there's some context, apples around, then there's a question, what shape are apples, and then it gives an answer that apples are square. And like even small models kind of learn to lie about fruits. But then if you're like, are you sure? like small models will kind of say nonsense or whatever, but
Sorry.
this should say 3.5, sorry.
How do you separate this from GPT-4 or whatever model
Mhm.
actually changing its ground state
Yeah.
knowledge form?
Yeah, so one thing we also do in this paper is that we have this other method of assessing beliefs where it's supposed to be, essentially we like give the model some scenario that's designed to get it to reveal its belief. So it like gets a scenario and then has to choose one of two options, and it should choose like one of the options if it believes X and the other option if it believes not X. So we kind of show that, yeah, in these scenarios, its beliefs are still like consistent. And this is supposed to be like a step towards honeypotting the models, essentially. But then in these like particular interactions, they lie and then reaffirm their lies.
In one, it's like a user's asking questions, and in the other, there's some other. It's not. You're not asking it for knowledge about the world. It's like eliciting knowledge in some other way.
Yeah.
Is that right?
Yeah.
So the thing it's learned to deceive people about fruit when they're asking questions about fruit or something.
Yeah. So actually, it was kind of the actual result is that they're like inconsistent in scenarios, or at least GPT 3.5 is like inconsistent in scenarios. So there's like, yeah, I think it's maybe like unclear whether it rewrote all its beliefs or whether it like learned to lie about fruits. I'm not sure how you would assess that. Yeah, this is just a plot of like lie reaffirmation rates. So they learn to essentially reaffirm lies and correct truthful answers about fruits. I think it probably didn't rewrite its beliefs about fruits because lying generalizes to like fruits it hasn't seen. So unless it like rewrote all its beliefs about like all types of fruits and like even fruits that we make up, that seems unlikely.
But your characterization of belief, I don't quite remember it, but if someone always lied about that thing, wouldn't that mean that they believe it according to definition?
Yeah, so here, like specifically, models, sure. I think I'll come back to this at the end because I have 2 minutes. So let me briefly wrap up. Okay, I only have the conclusion slide anyway. Summary, we formalize deception in SCGs. Under some assumption, you can apply this theory to language models. And yeah, I guess one open problem that I often think about as something that I want to hand over to interpretability people is like, what does it mean for an agent to have a subjective causal model, and how do you get that out of the thing, essentially? Yeah, that's it.